Greetings and welcome back to Chapter 14, where today we will be discussing fluid dynamics, continuing on from pressure from last time. Air is a fluid, just like all other gases, so liquids and gases are fluids. As a result, there is some pressure from the atmosphere, right? Because it is a fluid with some fluid density. The amount of air pressure at sea level is about 101.3 kilopascals. We also call this 1 bar. The bar came from the term from the barometer that Torricelli built to measure atmospheric pressure. And when he built this barometer, it lifted mercury something like 760 millimeters. Now, mercury is about 13.6 times as dense as water, and so if you wanted to make a barometer out of water, it would have to lift the water something like 10.3 meters by atmospheric pressure, 3 stories, something like that. Which is why typically we use mercury, right, for pressure, for barometry. Now, we've probably all seen this before. I don't know if I want to use this pen. The ideal gas law. Now, if you have some gas that's enclosed, right, it follows this kind of relationship. That is, the pressure, I'm sorry, it's supposed to be a lowercase n. The pressure times the volume inside a container is equal to the number of moles of gas. Remember, moles are 6.02 times 10 to the 23rd, or 1 Avogadro's number of particles, times this funny thing, which is just the ideal gas constant, 8.314. But don't worry, I will always give you this if you have an exam question or something like that within it. And this last T here, anyway, is temperature. And we have to be really careful. Typically, when you make any kind of temperature reading like this, you have to use absolute temperature, and that, of course, is the Kelvin scale. But we'll come back to that next week when we talk about temperature and begin to get into thermodynamics. Now, if you have some gas that's enclosed, right? If you have some gas that's in a balloon or whatever, then the number of moles of gas are going to remain constant. Let's say that you have an enclosure that's got a temperature reservoir, like a refrigerator, so that everything in it remains the same temperature, right? That means nothing on this side is going to change. The number of gas, if it's enclosed, nothing getting in or out, is not going to change. The temperature is not going to change if you have a temperature reservoir, right? And this is just a constant, it's just a number. That's obviously not going to change. So, that means you'd have pressure times volume is equal to a constant. Now, let's say that you had some gas that was enclosed in this enclosure with a steady temperature. But then you change the volume to about half its size. So then you're going to have some initial pressure and volume, and then you're going to have some final pressure and volume, right? Well, if you're going to shrink the volume to half its size, the pressure has to double in order to compensate. This is called Boyle's law, B-O-Y-L-E. Do we experience a buoyant force in air? Well, obviously we have to, right? Air is a fluid. And if we're immersed in a fluid, we have to experience a buoyant force. But how much is it? Well, obviously it's going to be equal to the weight of the air that we displace, right? The density of the air times our volume times gravity. Air, let's write this here maybe. the density of air is not a tremendous amount. It's about 1.25 kilograms per cubic meter. That's kind of a lot, right? Cubic meter, it's a very large enclosure. 1.25 kilograms, however, is not a very large mass. So the density of air is not a whole lot. But it's also not zero. And so the buoyant force that we're going to experience in air is not going to be zero. So how is it that hot air balloons work then? Well, obviously a hot air balloon displaces a lot of air, right? The air in the balloon is heated so that it expands, and it becomes less dense than the rest of the air outside of the balloon, and it rises. If the overall density of the balloon in the basket is less than the air, then the balloon can take off, right? Because if something has a lesser density than the fluid that it's immersed in, it will have a positive buoyant force. Positive net force. Obviously, a buoyant force is always positive or upward. Now, consider, if you will, some water going through a pipe. Okay? You got some water going through a pipe. Right? Here's your pipe. Here's your water. And the water is moving along this way. Okay? Now, let's say the pipe narrows. What's going to happen? Well, either the water has to bunch up or the water has to move faster, right? Because you've got a certain amount of volume here, and the pipe gets narrow, so the volume here is smaller. And so to keep the same flow going, the water has to move faster down this narrower pipe, right? But water going downhill to a lower altitude also makes it go faster, right? So like if this pipe went down, it would go even faster than that, right? What if instead the pipe went uphill? So here we got some water moving along, and then it goes in an air tube and it goes really fast. And then it goes uphill and it slows down, and by the time it comes out, it's not moving as fast, right? That kind of sounds like conservation of energy, right? Gravitational potential energy. Obviously, if something is moving uphill, it's going to slow down, and moving downhill, it's going to speed up. Also, if the speed increases, the internal pressure inside the fluid decreases, because if you want to think about it this way, if you got a balloon, right? Now, the particles in the balloon are kind of moving around in all random directions, this way, that way, that way, that way, and they're all banging into the walls of the balloon, and that's what keeps it inflated. And so it's the fact that it's random and always applying force to the sides of the balloon that give it a higher pressure, right? A high enough pressure to keep it inflated. But if all of that air just kind of went in one direction, the balloon would deflate, right? And so there's not as much pressure on the pipe, say here, from particles going up and down. Most of the particles are going this way, down the pipe, right? And so if the speed increases, the internal pressure in a fluid decreases. This is called Bernoulli's principle, and we typically write it like this. Say 1/2 mv1 squared plus rho g h1 plus p1 times v is equal to 1/2 mv2 squared plus rho gh2 plus p2v. This term, the 1/2 mv squared, that's obviously kinetic energy, right? This is potential energy, rho gh, right? We're talking about gravitational potential energy, or the amount of pressure in a fluid, right? And here we have pressure times volume. And so essentially, if something speeds up, the internal pressure has to decrease, right? If something goes uphill, then its velocity will decrease, but it'll gain gravitational potential energy, right? And so if you're going uphill or downhill, or in a narrower tube, or moving faster, or however you want to say it, you can figure out what your internal pressure can be from this equation. In any case, I hope you've enjoyed today's lecture. I'll see you again soon for Chapter 15.